You should see the lecture notes published. Okay, so welcome back, everybody. We're getting closer to starting on time every week. So the microphone is working. Is that right, Amin? Actually, let me quickly make you a co-host, and then if anything comes up in the chat, etc., you can do it. Let's see. Okay, so you're a co-host now. Sound good? Okay, so we were talking about compute models last week. Just a few more things to finish off on that. Let's see. So I didn't quite finish. So the last compute model we were talking about was the cellular automata compute model, where basically your data is on grid elements and your operators are also basically on grid elements. You're doing local computations like differences and averages and so on the things around you to update. So this is a picture of a finite difference time domain for electromagnetics, so just directly discretizing the calculus equations. So you can take calculus equations, which are differentials, and turn them into differences, which are an approximation of a differential, and you can solve them by just repeatedly finding all the differences, for example, of the electric fields to figure out what the magnetic fields are in the next time step. Then you use all differences of the magnetic fields to figure out the electric fields after that, and so on. So this is showing how the electric fields, shown in red, are at various grid points, and the magnetic fields, shown in purple, are also at various grid points and in various directions. And this is an example of a simulation of a horn antenna. Does anybody know what a horn antenna is? These guys are probably computer engineering side. This is pretty hardcore electrical engineering. It's just an antenna that there's a waveguide. So like say a coaxial cable or a rectangular box that's bringing electromagnetic, very high frequency electromagnetic signals into that end of this horn. It looks kind of like an audio horn. And it basically guides the radiation and creates a pattern of radiation that goes out that way. So it's directional. It's good if you want to have a signal that goes to a specific cell phone, from one radio tower to another, for example. So if we simulate the electromagnetic wave as it hits this, that far end of that horn, and then we trace forward in time and keep updating through the whole of space, we figure out what the radiation pattern looks like. And this is showing the radiation pattern is basically strongest straightforward with some radiation going out to the sides. And if you're an antenna engineer, this is what you care about. So we talked about how if we were able to put all of the grid points in an FPGA at once, so different little regions of the chip were each responsible for different little pieces of this geometry, it's going to be unbelievably fast, right? We've distributed our storage, we've distributed our operators, but we probably couldn't do something as big as this. So to model this whole antenna, we might have, I don't know, 100,000 or 1 million the grid points. So that's probably too big to fit on our FPGA. So we talked about, well, we could, instead of trying to put the whole geometry in the FPGA, we could put a piece of the grid in the FPGA and kind of stream data through it, and then stream a new piece of data through and so on. So it's kind of like streaming, and it's pretty efficient. Good for physics equations. Okay, so that was our last compute model. Let's just talk about how these compute models impact design tools. So compute models are a way to think about organizing your computation for efficiency, but they're also a way to think about how would I program this. And they don't go together in lockstep. Like the decision of what compute model to use doesn't determine I must now use this exact design tool, but it does make some design tools easier than others. So, okay, so the method of computation that you choose affects your efficiency, but it also affects how you develop your design. So in general hardware, you can write it in HDL. So you can kind of do anything in HDL. HDL presents, again, that compute model of communicating sequential processes. So a very general compute model is what VHDL and Verilog are showing you. So if you just think, can I write it in VHDL or Verilog? The answer is basically yes. You can write anything, any compute model. But writing in hardware description languages is more time-consuming, more low-level than writing in languages like C. So you can also use high-level synthesis tools to go from a C, usually a C-like language, into hardware blocks. Okay? So who here has used a high-level synthesis tool? Okay, so a couple people. What's the definition of high-level synthesis versus HDL? So I know what my definition is, which I think is pretty common. But like, what makes something a high-level synthesis tool instead of VHDL or Verilog, which are also programming languages, but they're not considered high-level synthesis? So why? Why is some particular representation high-level synthesis, whereas we don't consider Verilog or VHDL high-level synthesis? What do you think? What's the dividing line? Yeah?
You can do similar things to like programming languages that can have visual science and hardware?
Yeah, so the idea is that it is a little higher level. It's a little, I mean, all of this stuff is in a sense programming, but a high-level synthesis language, yeah, they have some more constructs that are more, it looks more like C with some annotations. There's no standard, okay? So high-level synthesis, there are a lot of different tools. The most common type uses a C-like syntax or C syntax exactly, which usually is not enough information to generate efficient hardware, so then they add in some pragmas, some extra guidance to the tool to try to tell it how to generate hardware. It's actually a bit unfortunate because there is no standard. It means you learn one tool and you learn the ins and outs of using it, and if you move to a different vendor or a different tool, some of that knowledge is lost. So that actually is unfortunate, but it's the way it is. So it is more software-like. The definition that I use is it's without clocks, okay? So in hardware description languages, you are saying, here are my registers. There are clocks. So you're deciding what goes in a clock period. In a high-level synthesis tool, you will not see a clock. You will see for loops. You will see computations. You will see pragmas that say things like, do this in parallel or pipeline this loop. So you'll see like things like pragma pipeline, pragma parallel. But you will not see clocks. So the tool decides, where am I going to put the registers, which defines where are my clocks. Does that make sense? Okay, and there are courses here at U of T that use high-level synthesis, so if you want to get some expertise in that, you can do that. Soft processors. So I guess general hardware, you can always write an HDL, and it gives you the most control, and you can do anything. You can also do a fair amount of hardware in high-level synthesis. It is generally faster than writing HDL, like takes less lines of code. It does give you somewhat less control, so you're kind of trading productivity for somewhat less control. And the other thing, as I said, that's a bit unfortunate about it is also kind of lack of portability. Like what you write in one high-level synthesis tool generally will not move to another high-level synthesis tool, so you're a bit more locked in, whereas HDL is pretty standard. The output of a high-level synthesis tool is HDL. So HDL is kind of like the assembly language of FPGAs. You can write it directly. You can have other tools output it. Another way you can describe your computation is a soft processor. So for a soft processor, you write in typically C, right? You write in a language that can be compiled into instructions. And then, as we talked about last week, we're commonly adding coprocessors to that. And we can write those coprocessors in a hardware description language. Streaming data flow. So we can do that in HDL, and it is done a lot in HDL, so many people write their streaming data flow that way. But we also have some domain-specific higher-level synthesis tools. Does anybody know what I mean by domain-specific? What's that mean? You can sort of remove the hyphen and repeat it back to me, and it's kind of a reasonable answer. Like so, yeah. Yeah, so you're saying, yeah, so that's a good answer. So I'm going to just repeat that. So something like OpenCV, where it's about computer vision. So you make a tool that works for that domain, right? You're not saying it works for everything. You have some other computation that's not computer vision. You're not making any claims that you can even describe it in this tool, or certainly not that it'll get reasonable results. You're saying that for this particular area, this tool is going to do a pretty good job, and you can use it at a higher level than HDL. So there are a bunch of these domain-specific tools. Okay, and I already said this. HDL is like FPGA assembly code. It is Some of it's written by hand. A lot more HDL is written by hand than assembly code is written by hand. So people don't write assembly code very much anymore. They do write a lot of HDL still. And it's generally what all these other tools output as well. So that's what you stick together if you have some high-level synthesis modules and some things you wrote by hand. Yeah?
Regarding the second point, do you literally write it in C, or is it again a C-like language?
Which one are you talking about? Soft processors?
Yeah,
Soft processors are an instruction set processor, so you literally write in C. It's the same C that you would write for an embedded processor that if you bought it, or if it's a hard processor on the FPGA. So right, you can buy lots of FPGAs with a hard processor in them. You can write assembly language for them as well, but usually you write most of your control code in C, and it will compile down to that processor just as if it was an x86 processor.
So that's the software running on the processor.
Yeah, so that's the software running on the soft processor. Usually you write your own software. You could make your own soft processor, but you also, and you do that for something called overlays, where you make very unusual soft processors. But if you're making a very conventional one, I just want to run normal C programs, usually use Neos or RISC-V or Microblaze. You just get it from one of the vendors and they wrote the RTL, you compile it, and then you write C to run on top of it. And then you might go, well, but I really need some hardware acceleration working with it, so then you're writing those coprocessors, and those you write in HDL. Does that make sense? And the way you control those coprocessors is typically the processor is writing to registers, which you can do easily in C. So you're writing the specific memory addresses, which correspond to registers on your on-chip AXI bus, and that all you could do from C. Does that make sense? Okay, so high-level synthesis. So I guess I talked about this a bit already. So your input for high-level synthesis is some untimed algorithm description. So you don't specify the clock cycles. There are a lot of variations of high-level synthesis, like what's the input? I mean, the output's always basically HDL. Often HDL that's really hard to read, but it is HDL that goes into the rest of the FPGA CAD tools. But the most common is some variation on C, where you've added in extensions, or meaning like you've added in extra constructs to the language, or more commonly, people often added in extra constructs in some of the early high-level synthesis tools. Now they usually add pragmas. With a pragma, what it means is inside your code, you see literally hashtag pragma, and then something. Like you might say hashtag pragma pipeline. Okay, and then underneath that, you have a for loop, and that tells the compiler this for loop is actually a good candidate for making pipelined hardware. So you gave it a hint. Okay? The nice thing about pragmas is all C and C++, etc. compilers will ignore pragmas they don't understand. So this means that you could still take your code and run it through a software compiler, and you will get a program that runs. It doesn't make hardware, but it'll run. So that's the nice thing about pragmas. A compiler that doesn't understand them ignores them, which means you can still run your software on a CPU just to see if it gets the right answer. Okay, that's not your end goal. Your end goal is you're putting all these pragmas in, using a special tool to turn it into HDL, like Verilog, and you're trying to get higher performance. That's why usually high-level synthesis tools now use pragmas rather than just making up constructs, like making up new keywords in the language. Because if they make up new keywords, you can't actually compile that code in a conventional compiler at all. Okay, the output, as I said, is HDL with the clocks put in. And there's a lot of cleverness that goes into this. So popular versions of this, both Xilinx and Intel have high-level synthesis tools. So it's basically C with these pragmas. And what those ones are targeted at is basically making blocks. So they don't try to make an entire design, but you might have, for example, a finite impulse response filter, or maybe that quadratic equation that I showed as an example. You might be just trying to take that much code and make it into hardware. So you're not trying to describe your whole system. Usually it's like some hardware block of kind of moderate size. And then you're going to hook that up to the rest of your hardware. There's another variation on high-level synthesis, which uses OpenCL, and both Intel and Xilinx have this as well. Who's familiar with OpenCL? You heard of this? Okay, so OpenCL is basically a competitor to Cuda. Who's heard of Cuda? Okay, so Cuda is NVIDIA's parallel version of C that runs on their GPUs. It's proprietary to NVIDIA. NVIDIA's done a great job of building Cuda, and it's a huge barrier to entry for everybody else trying to write, will try to make a GPU, right? Because NVIDIA has this version of parallel C that runs on their GPUs that is quite popular, okay? So that's Cuda. OpenCL is like the open standard competitor to Cuda. It is basically C with parallelism expressed, and the parallelism is expressed in a way that is essentially like Cuda, okay, where you have lots of little threads. And that works well for GPUs, but it also turns out you can make a software program that takes that as input, because it's basically C with a certain style of explicit parallelism. The parallelism is written into the program, and turn that into hardware. So instead of needing pragmas that say how to interpret the C for parallelism, you basically use the fact that there are lots of threads and the parallelism is expressed in that way. And you can turn that into hardware as well. So under the hood, it turns out that the software tools that are doing this actually share a lot of code, right? So I know how the OpenCL compiler for Intel works, because it was created in my team while I was there. And the code base, a lot of the code base is shared between these two use cases. But basically, when you use the OpenCL version, I guess it's basically a little more standard, because you're using fewer pragmas and more of this parallel C language that is friendly for GPUs. And the other thing is, in OpenCL, you don't just write one hardware block. You basically write your whole system. You can write, here are the kernels. The kernels are the parallel parts that in a GPU would run fast, and in a hardware compile will go to hardware. But you also write what's called the host code, which is basically just the serial C that sets everything up. And that will run on either a hard processor or a soft processor or maybe an x86 processor across the PCIe bus, and kind of set everything up and just do the lower bandwidth computations. So the nice thing about OpenCL is it kind of like lets you write all that in one unified program that is fairly standard, rather than having to kind of make it all up yourself. Does that make sense? Okay, so there's lots of different ways to do this stuff. So, okay, so let's talk about, I'm going to talk about a domain-specific high-level synthesis tool. And this high-level synthesis tool is useful for streaming data flow. Streaming data flow, as we saw, is useful for, well, one of the things it's really good for is signal processing. Signal processing maps really well to a streaming data flow compute model. So you can go write in HDL your streaming data flow, and in fact, you're doing that in lab 1. You'll do a bit more of it in lab 2. But it turns out there are a lot of signal processing engineers who use Simulink. Who knows what Simulink is? Who's maybe used it in undergrad? So what is Simulink? I'm going to pick on you. So you forgot? Okay, no worries. I still appreciate putting your hand up. You know what? You're still in the top 10%, right? So because you're familiar with it at least. Yeah, what do you think? Yeah, it's related to MATLAB. So Simulink is basically like a flowcharting tool that signal processing engineers use a lot. So I'm showing here a little flowchart of basically it's a filter, and the filter goes into, I don't know, a covariance estimator and various other signal processing blocks that are hard for me to read right now. So if I'm a communications engineer, I'm trying to figure out what's a good modulation scheme for my wireless communication system. So I can stick filters down, I've got channel responses, I've got noise. I can put all that in Simulink, and basically with just flowcharts, and then I can run simulations to see, you know, what's my signal to noise ratio, what's my bit error rate, etc. And I can tweak. Maybe I need to change my modulation or my coding, or do what-if analyses with different kinds of noise. And this is how I come up with new communication protocols. So this is commonly used by an important market for FPGAs, people designing signal processing algorithms. So both Xilinx, which is now AMD, and Intel have tools that can go straight from a Simulink block diagram, something like what I've shown here, to hardware, because they basically want to reduce friction for this class of people who are, potential users of FPGAs. Those people don't really want to go write HDL, but they're already in Simulink modeling their system. Okay, so from a block diagram like this, so in this case, the input to the high-level synthesis is not C with a bunch of extra pragmas or OpenCL constructs. It's actually a block diagram. But for every one of the important blocks in Simulink for signal processing, Intel, for example, has gone off and written an IP core. IP core means intellectual property core. It just means a block of parameterized hardware. Behind the scenes, it's a bunch of HDL, but you didn't write the HDL, you just asked for it. So it's like a library call, but for hardware. So, and they've written a bunch of these, right? So every one of these little blocks that I've shown here basically maps to some IP component. And they may not do every single thing that's available in Simulink, but they try to cover like the major ones. Okay, so I'm just going to show you a few figures from my time at Altera that showed how to this, an example of using this. Okay, so you give a little bit of extra information. So this is actually a little bit of extra information that you give to the hardware generator, saying, what's my target clock frequency? What data width do I want? So I want to use 32-bit data. I think that's enough for my accuracy, and so on. Okay, you enter the design by just making that flow chart and entering little bits of extra information, like clock frequencies and data widths. And this particular example here is just like, this is a finite impulse response filter. Okay, so that's filtering. This is doing some scaling. This is doing some interpolation, so increasing the data rate by averaging between samples and putting more samples in, some more scaling, some more filtering and interpolating. I am not a signal processing engineer, so I can't actually give you a whole lot more detail than that. But this is basically somebody trying to create a signal or a system for part of a wireless receiver, for example. Well, this one is actually a up converter, so this is like part of the transmission channel for a certain wireless networking standard. Okay, so they enter the target Fmax, so this one they said 179, and they just press play. And it generates RTL. Okay, so the programming model is just block diagrams in a stream tool. So you're putting down block diagrams in Simulink. Every one of those is like processing on a stream of data. So the compute model that this maps to behind the scenes, what is Intel or Xilinx has a similar tool doing? They're basically using synchronous data flow. So one of the compute models that we talked about. So is a bunch of data flowing through a pipeline of spatial operators. So basically every one of these things turns into a hardware unit that's going to go in a different part of the FPGA. And it's deeply pipelined, so lots of pipeline registers. And they mark the data with valid bits, just like we talked about. And that gives them decentralized control, right? By having valid bits, it means that all these IP blocks are kind of just figuring out themselves without any global controller. Is my output valid or not? When do I have all my inputs ready, and therefore I can compute my output? In this particular case, there are some parts where there are back pressure, but most of the data path actually doesn't use back pressure. So the tool analyzes, could this module ever not keep up with its inputs? And if there's no chance of that, they don't put back pressure in. Okay, so it only puts back pressure in when it needs to. It only puts buffering in when it needs to. So it kind of uses the simpler form of synchronous data flow where you don't have back pressure for most of the data path, but there can be parts where it needs it. In that case, it will use the more complicated form of data flow, somewhat less efficient form of data flow with buffering and back pressure. The tool analyzes your flow of data through this, and it automatically, basically in order to keep the throughput matched, to make sure that this block, for example, can keep up with what's coming into it, it will automatically make it more parallel if it has to. It'll basically widen the data path if it needs to in order to keep up with the block before it. Okay? So yeah, for example, you might have a 16-bit data path in parts of this, and at some points that might not be enough. You can't keep up, so it doubles it and widens it out to 32 which can handle sort of 2 data items at a time. So it's got twice the throughput and can keep up. And in this particular tool, clock frequency is a constraint. So the user just says, I want to run at this clock frequency. And the tool retimes and repipelines. So in this case, the input is high enough level, right? It's just these signal processing block diagrams that the tool can actually add pipeline registers, because you haven't specified anything about the exact latency. And all of these IP cores basically they have some control over the amount of pipelining that goes into them. The tool also can add pipeline registers, like just extra registers in between these blocks. And because they all have valid signals on them, it's okay if the latency changes. The control logic will still all be correct. Everybody still knows when their data arrives because they just check the valid bits. So it can repipeline them, and it also retimes it. So first it puts more registers in, and then it moves them around until it hits this frequency. So this is sometimes called the latency tolerant design. Okay, so if you use, it's one of the nice things about using some of those streaming data flow models that we talked about. They don't have central control logic. They just negotiate based on, are all my inputs valid? What to do next? Do I compute an output? That makes them tolerant of changing their latency. They don't break if you change it. So it makes it much easier for a tool like this to change the pipelining and have it still all work. If there was some central controller that was counting clock cycles, changing the pipelining anywhere would just break the design. Okay, so the analysis I saw of this tool was in Stratix 4, which is like a 40 nanometer FPGA, so it's not as fast as the latest ones. But in that FPGA, you could reliably hit 400 megahertz for these signal processing designs, which means in like the latest FPGAs, you could probably hit about 800. So this is actually pretty good. This is actually beyond what most human designers could do. And the alternative, Altera actually built this twice. They built it in 2 different ways. So the one I just talked about, the whole data path runs at 1 frequency. And if you need more throughput for a certain part of it, you widen the data path. So you don't try to clock that IP block faster. You just basically put a couple copies in and widen the data path out. And they pipeline the heck out of everything in order to try to get a really high clock frequency. And that turned out to be significantly more efficient than the alternative approach, which was to actually take these different IP blocks and try to run them each at whatever was their maximum frequency and hook them all together. That didn't work as well as just picking a frequency and pipelining heavily to make that fast and just tying them all together on the same clock frequency. So anyway, so it was interesting. And that kind of related to a question someone asked a couple lectures ago about would it be a good idea to make different IP blocks run at different frequencies? It does happen all the time. But in this case, for streaming data flow, this was an example that showed if you can pipeline enough, it's actually better just to tie everybody together. Let's see. The other thing this does is we talked about an optimization you can do in streaming data flow is if your operators, so these operators are IP cores. Someone else wrote them. You're just sticking them in your Simulink block diagram. So if some of them have more throughput than you need, this tool will time domain multiplex them using the technique that we talked about, basically putting a channel tag on them. So throughout the data path, all these IP blocks send obviously the data, which might be 16 or 32 or 128 bits wide, a valid bit, okay, which is what makes them latency tolerant. They can tell when their inputs are valid and not valid, and a channel identifier. And by setting a channel identifier, it means they can now multiplex multiple channels together if they've got a really fast IP block. And this commonly, as I said, this commonly actually outperforms hand-coded HDL, which is not the usual case for high-level synthesis. So usually when you go to high-level synthesis, you don't put your clocks in, you don't write your Verilog, you get your job done faster, but the resulting hardware is not as efficient. In this case, because the input block diagram is kind of from a certain domain, it's from signal processing, it's feed forward. We know this is feed forward without a whole bunch of loops in it. It's mapped to this streaming data flow that is known to be very efficient for that. Tool automatically pipelines and retimes and actually outperforms what the typical human can do. But that's basically because it's specialized to a certain domain. right? It knows a lot about the kind of hardware that is efficient for this, and that makes it easier. If you want to know about Xilinx's version of this tool, because they have a competitor to this called System Generator, Chapter 8 of the Reconfigure Real Computing book talks about it. Okay, any questions about that? So it's kind of a digression on high-level synthesis and when you might use some of these tools. Okay, so another few tools, software and coprocessor tools. Okay, so another program model we talked about was we make a software a processor. Maybe it's hard, maybe it's soft, and then we make coprocessors for it. So the one way you can do this is you write your software code, usually in C. You build the accelerators in HDL, or maybe you can find them in an IP library. So you might buy them, or maybe they came with the CAD tool. And then you can integrate them with the processor by writing buses in HDL. So I said usually you interface with Avalon or AXI buses, these on-chip buses. Their protocols are fully documented. You could write HDL that implements them. But this is kind of a pain, right? You're kind of writing essentially a bunch of very detailed glue logic. So more commonly, instead of doing that by hand, use a system integration tool that you take your IP cores, one of which is your soft processor, and you just tell the system integration tool, I want this soft processor, I want these two coprocessors that came from your IP library, this other coprocessor that I wrote myself, wire them all together for me, and give me some memory addresses I can write to control them. And both Intel and Xilinx have tools to do that, right? So Intel calls theirs platform designer, Xilinx calls theirs IP integrator. And yeah, so that just saves you work. Instead of having to write these buses, you can just block diagram your system, and this tool will generate the HDL for you that builds all those on-chip buses. Xilinx has a tool called Sdsoc. I forget what it stands for. Maybe if there's anybody from AMD, you can say what that stands for. It's not super memorable. So the SoC, I'm sure, is S, system on a chip, and I forget, I think maybe SD is software defined or something. They have a pretty cool tool in that where you write just an application, you take your application as written in C or C++, you run it on a hard or soft processor, they profile it, so they figure out where the time's going, and they basically just mark on the software code, here's where your hotspots are, here's where most of your time goes. You can actually then, in their GUI, mark those hotspot functions to be hardware accelerated. So you just say, okay, that function came up as 80% of my CPU time. I want that to be hardware accelerated. They actually take that function that you've already described in C, and high-level synthesis turns it into hardware for you. As long as you wrote it in the high-level synthesis tools don't take all of C and C++. So some things, there are some complicated constructs that they'll just say, I don't know how to turn that into hardware. But as long as you use the subset that they support, you can turn it into hardware. It then runs it as a separate thread. So it kind of runs in parallel with your software, and you can talk to it. You can basically read and write from memory variables to lock or to synchronize with it. And they also generate the buses automatically to interface that hardware unit to the processor. So this is actually a very fast flow for a custom processor, right? You wrote your software, you profiled it, you marked certain things to be hardware accelerated, built you the buses, put it in a different thread, and basically you can handshake with it. You then probably have to go in and write some pragmas and do some tweaking of the software input to the high-level synthesis tool. It probably won't be fast enough if you don't do some optimization. But it still took a lot of the drudgery out of kind of connecting these things together. Okay, so that's it for just kind of a tour through some different design tools for FPGAs. Any questions on that? Okay, if not, let's go on to, that was kind of just finishing off what we were talking about last week. Let me discard my annotations. If you're worried, wait, does that mean lecture's over? Have no fear. It's not over. So, and if you were hoping that, sorry. So, but you are most of the way to a break, so I can give that to you. Let's see, let's try this. Let's not try that. And let's see if this is shared. Okay. Whoops, this is wrong. This should be Sunday. I just took a day off there. Okay, sorry about that. I'll correct that. Okay, so assignment 1's due on Sunday at the end of the day. 2 readings for this week, and hopefully we get to both of these today. For next week, 2 papers that I recommend you read, and then an optional one if you're kind of going, I'm loving these, let's read another one. I realize most people won't have time to read 3 papers in a week, but I don't know. Hope springs eternal. So first paper is not very related to FPGAs, frankly, but it's about basically doing good benchmarking. So this first paper is a paper by Intel that does a very careful analysis of a bunch of applications that have been published where they claim very large speedups with GPUs. So they go through to try to check, are these speedups real versus a CPU? Some of you in your graduate research may be trying to speed up applications using GPUs or FPGAs, and this paper I think is a really good exercise in showing you got to be careful when you do that. You can't just take some C code that you wrote the last day of your degree and say that's the CPU result, and then in this case the GPU result is what I spent 2 years on, or the FPGA result I spent 2 years on, the CPU I wrote some C code in the last afternoon. So not directly talking about FPGAs, but talking about good benchmarking, which is important for lots of purposes. This paper is about work that Microsoft has done where they've put FPGAs in their data centers as programmable accelerators. Pretty interesting work about how you make massive scale parallelism using FPGAs and how you combine them with CPUs. And that's the second generation of architecture that Microsoft put in their data centers for FPGA acceleration. The first generation is this paper. So that's why I'm making it optional. I mean, these are all optional because you actually only have to do 10 of them. But I guess I'm making that double optional if you want to think of it that way. It's also a good paper, right? It's the prior generation. They built on that generation with this later paper. So you could say, look, just give me the highlights, tell me what worked, and you'll get that from that second paper. But this first paper is also, I think, a very nice analysis with a lot of good insights. So if you're kind of like, it's Thanksgiving Day, you're like, what am I going to do today? I'm going to read 3 papers. There you go, right? 3 papers for you. So it's your tuition dollars at work. It's a free bonus. So, okay, course concept map. So we've just been talking about, okay, FPGAs are a blank sheet of paper. What are some ways we can think about organizing computations? So that's what we're talking about for compute models. What we're going to talk about today is FPGAs versus other compute devices. So it's still kind of related to compute models because there are certain devices that essentially use different compute models. So a processor has one compute model, a GPU has a slightly different one. FPGAs are kind of unusual in that you can decide all sorts of compute models to stick into it. But basically, it's useful to know what are FPGAs good at and bad at. So it's kind of a deeper dive into some of the things we talked about in the first lecture of what are strengths and weaknesses of CPUs, GPUs, Dsp processors, and FPGAs, so that if you're trying to build a system, you have some rules of thumb about which of those might be good, okay? So I'm going to talk some about CPUs and GPUs and DSPs. I'm not going to go into huge detail on them because we have multiple courses on CPU architecture. We got a course on programming GPUs. So this subtopics here could each turn into multiple courses. So so I get detailed enough questions, I'm just going to send you to those profs, okay? So you can ask me some, and at some level I won't know. Okay, so let's compare these programmable devices from 10,000 feet. So we've got ASICs. We talked about those earlier. These ones are all programmable. So high-end CPU, okay, so there are multiple kinds of CPUs, right? There's low-cost ones that are relatively slow, low parallelism, but also low power and cheap. And then there are high-end CPUs that are intended to run programs fast. That's what I'm talking about here, but they're more expensive, more area, more power. So a high-end CPU, well, all CPUs start with, fetch and decode your instructions, right? They don't know what to do until they get an instruction. Then that instruction says, well, what do I do? So controls the ALU, it executes some operations. In order to make any progress, it has an execution context. So an execution context means what's in my registers, okay? And usually also cache memories. So, but in particular registers, the instructions are actually saying, what do I put into the registers? What do I take these two inputs from two different registers, add them together, put them back in another register. So that's the execution context. The execution context only stores a limited amount of data, so we also have to go to main memory a lot to load things into our context or registers. So we have main memory slow, so we have a data cache to keep recently accessed data values from memory, otherwise our processor is going to wait for memory all the time. And in processors, this is a big one, right? We spend a lot of die size on that. We're also trying to keep the processor busy, and in order to do that, there are a lot of things that could stall our processor, especially as we make it faster and faster. We're trying to pipeline it deeply so it's working on lots of instructions. We make it super scalar, which means we're actually launching multiple instructions every cycle. That means it's getting harder and harder for it to find work to do because the results of the previous instructions aren't ready yet. So we have out-of-order control logic. Does everybody know what that means? What does out-of-order control logic mean? Yeah.
While installed, you can do the next instruction or you keep going.
Yeah.
Question.
Yeah, so the processor is not executing the instructions in the order that you wrote them in your program, right? Or the order in which the compiler put them. It appears that it is, okay? When you're debugging it, you cannot tell that it's actually doing instructions out of order. But it has, a modern processor, high-end processor will have typically like 100 instructions in flight. So it's launching multiple instructions every cycle. It's got a pipeline that's maybe 30 cycles long. So it's got about 100 instructions that are partially done. And they actually, some of them are further in the program than others. They're not even launched in order. But it keeps track of all sorts of bookkeeping so that you cannot tell. It never updates this execution context with an instruction until it knows that instruction is the next one that should have been executed. Okay, that actually takes a fair amount of hardware. So this is quite complicated. Okay, figure out what is the next instruction or next instructions, because it's actually doing several per cycle that I should execute. Okay, you've got all sorts of if statements, right? So and that if statements mean jump over this code. Don't do this code, do that code. That is hard for a processor because it means I don't know what instructions to fetch. And I don't know what instructions to do next. And it's going to take me quite a few cycles before I know the answer to that. If I wait 10 cycles so that later in my pipeline I know the answer, well, I've just stalled this hugely expensive processor for 10 cycles, wasted tons of throughput. So they've got a branch predictor that before you actually know if X is less than Y, it's already guessed. Okay? And they spend a fair amount of hardware on that too, because they need to be very good at predicting those if statements or they're going to be stalled all the time. It has a memory prefetcher. So what is a memory prefetcher? Does anybody know what this is? I'm just doing CPU test questions. You know?
Move from data from memory to the cache.
Yeah. So the cache basically stores recently used data, which is useful. But for some kinds of computation, let's say I'm going through really big arrays and so on, which is common in these kind of streaming computations we're doing, it's not enough, right? Because you don't just reuse data. So you might have a lot of data, so the reuse isn't enough. And the prefetcher basically watches the pattern of addresses that you're loading and basically guesses what data might you want next. And before you ever ask for it, it's already put it in the cache. So that, again, you don't stall the program. Takes, let's see, main memory is around maybe 30 nanoseconds, 50 nanoseconds, depending on the type of memory to access. And a processor has got a clock period, if it's a high-end processor, maybe 300 picoseconds. So, you're talking 100, 200 cycles typically to get data back from main memory. That's a lot of cycles, especially if the processor can actually launch 4 instructions for every cycle. So if you actually waited for data to come back, you stalled the whole processor, you had several hundred instructions that could have issued in that time. So you don't want to do that. So the memory prefetcher is trying to, even if you're accessing large arrays, guess what you're doing next. It's tricky, because if it guesses wrong, it actually might take stuff out of the cache that you need later. So it can't do a perfect job. Anyway, this works remarkably well. Processors actually run very fast when you just give them a bunch of C code. But it does take a whole bunch of hardware. Their goal is to maximize single thread performance. So just you write C code and you just get good performance. I mean, this is gradually, they do want to maximize single thread performance, but processors have also started to worry about maximizing somewhat multi-thread performance. So we now have multiple cores. This 24 actually is even higher now, but from about 4 to 60 cores on a single chip, depending on which processor, and are you talking server versus laptop? And every core is basically like a little processor that just shares the memory subsystem. They also use SIMD. Okay, so all modern high-end processors also support SIMD. Do you know what I mean by that? We talked about SIMD. What do you think I mean here? Yeah, go ahead. Yeah. Yeah, so with SIMD in particular is basically instead of taking 2 values, 32-bit values from this register, and one instruction says add them together, a SIMD instruction might say take 16 32-bit values from here, 16 32-bit values from here, and add pairs of them together. So we get one instruction doing much more work. So, okay, so they are focused on single thread performance, but they are adding in some things to improve throughput. Multiple cores and SIMD. Okay, so that's a processor from a modern processor from a high level. What about a graphics processor? So graphics processor is still a processor, okay? It still fetches and decodes instructions, but it makes different trade-offs. So it has simple control. So a high-end x86 processor has very complicated control, all this out-of-order execution, etc. A graphics processor doesn't try to do that. There's no out-of-order execution. It's going to execute the instructions in the order that you gave it to them. Okay? It doesn't make any attempt to figure out what to do next if it stalls. It uses SIMD heavily. Okay? So processors use SIMD, GPUs use it even more. And that's to basically make sure that I've got lots of ALUs that are all being controlled by one instruction unit. In a processor, they basically add SIMD. So they have some regular instructions and some SIMD instructions. In a GPU, the focus are the SIMD instructions. Like those are the main instructions they're trying to optimize. It's multi-threaded. So the way it keeps its execution units busy is not by trying to guess what instruction to do next. It's by having lots of threads, so it's just constantly switching to a different thread. So do a little bit on this thread with these instructions, then switch to another thread, do a little bit on those instructions, switch back to the first thread. And the programmer is much more responsible for just organizing where the data is. In a processor, you have hardware prefetchers, you have big caches, so the programmer, a really good programmer is thinking about, is this a big data structure or not, but you don't really manage the caches. In GPUs, the programmer is actually moving the data around, like deciding put this data here, put this data there, in order to ensure it keeps the execution units busy. And these are not targeted at single thread performance, meaning just a regular C program you want to run as fast as possible. They're targeted at throughput. I've got a lot of parallelism in my application. I want to get a lot of work done on many parallel threads. That's what their goal is. The reason that came from the graphics world, so this is now used for deep learning and all sorts of compute acceleration. The reason it came from graphics is if you think of what you're doing when you're drawing graphics, you're trying to figure out the value of 1 million pixels, and those pixels are largely independent. So that's why graphics processors went to this architecture of I can have a whole lot of threads. Every thread is figuring out what value a certain pixel has. And I can run them all together and just be switching between them if one of them's not ready, because its data's not ready. Because in the end, I need to make all million pixels, right? No one cares about making this pixel super fast and all the other ones aren't done. They only care when I'm done a million pixels. So GPUs are fundamentally, batch or throughput oriented. Turns out that also matches things like deep learning pretty well. Does that make sense? Okay, so there's some differences between CPUs and GPUs, but they're both processors, but there's also some convergence. So CPUs have been adding more and more cores, more floating point units, and more threads, which is kind of moving them more towards throughput computing, right? That's not about generally getting a better answer for one particular C program. It's about getting a lot of data through. So depending on what processor you're talking about, you usually have about 4 to 64 cores. So 4 might be a low power laptop chip. 64 is like the biggest, heaviest, most expensive server chips. They all have SIMD instructions. So, so the most instructions in a typical C program are not SIMD, but some fancy compilers can now start to recognize vectors and turn those into SIMD instructions. So you have a for loop over 16 things, and instead of doing 16 different little instructions to add 2 numbers together, it recognizes, hey, I could do one SIMD instruction. Compilers are gradually getting better. Sometimes programmers often they have to manually insert these instructions though too. So SIMD has been gradually getting wider. So originally processors had, like a mainstream processor had no SIMD. And then quite a while ago, probably about, this is during my PhD, so it's probably like 30 years ago, Intel, I'll just use Intel as an example, they brought in MMX, which meant that they could do SIMD on a few integers, okay? Then they brought in SSE, which can do 4 single precision floating point operations with 1 instruction, so 4-way SIMD. Then they increased that with AVX2 to 8-way SIMD, so 8 floating point operations can be done in parallel. And most recently, they've gone to 16-way, okay? If you use narrower operations, so there are 16-bit floating point representations, and there are 16-bit integers, obviously. Something that's 16-bit, the same data path can do twice as many operands. So if you use narrower data widths, they've also put in circuitry in the processor that basically your SIMD gets more SIMD. So with this most recent AVX 512, you can do 16-way SIMD for 32-bit floats. But if you were going to do 16-bit floats, which is something that's useful for deep learning, it's not very useful for general computation, or you're doing 16-bit integers, then you get 32 of them in every instruction instead of 16 of them. Does that make sense? So wider and wider SIMD. Interestingly, it has some impacts. Like when you actually use these AVX 512 instructions, you're doing so much computation that it tends to increase the heat dissipation of the processor, and it has to actually drop its clock frequency. So there are some trade-offs here. You still get more done, but it's not perfectly linear because these chips are still power consumption constrained, so they actually have to drop their clock frequency if you do that many operations per cycle. Let's see. Okay, and they have a little bit of ability to switch threads. So when you program these, if you have lots of cores, you try to write many threads in your software to keep the various cores used. Or in a server, you may have many different programs running, which means you got lots of threads because you got lots of programs running. So that's why servers tend to like high core counts. It's easier to use. They also have a small ability in one processor to switch between threads in one core. So we talked about, we have all this out of order control logic and balance prediction and so on to try to keep the processor busy. Despite all that, it's hard to keep all of its execution units busy, have enough instructions ready. So what most high-end processors do, certainly Intel and AMD both do this, is they have 2-way hyperthreading. Does anybody know what hyperthreading is? You've heard of this term? So you've heard it. Do you want to? I'm going to put you on the spot, but do you want to define what it is?
So while you're running one program, if you're stuck somewhere, you set up
Yeah, so that's exactly right. So what hyperthreading means, it's a form of multi-threading again. Remember when we were doing streaming compute models? We said if we had a really fast IP core, that we couldn't keep busy with one data stream, we could send in 2 data streams and just put a tag in saying you're from data stream 1 or you're from data stream 2. And then after we went through that IP block or that hardware block, we could take the streams apart again. Well, that's what hyperthreading is for a processor. Instead of having one pool of instructions, like it's just looking with a window, because they look at with a window of maybe 100 or 200 instructions, looking for things that are ready to work, ready to go to the execution units. Instead of doing that on one program, they basically say, I can do that on 2 different threads. So 2 programs, 2 threads. They have to tag them, okay? So every instruction now has a little tag saying you came from thread 1 or you came from thread 2. But the instruction issue logic is looking at basically both of them. It's looking at both those threads at the same time and seeing which instructions are ready to launch. And it means it's actually interleaving 2 distinct threads, which could even be from 2 distinct programs at the same time. Does that make sense? So it's looking and seeing what's ready to go, sending them to the execution units, and they're all tagged so that you make sure that they kind of don't start writing over each other's registers and so on. This typically gets maybe 1.5x the throughput. It's not as good as having 2 cores because you're still sharing the same execution units. But depending on exactly what the threads are doing, it's pretty common that you can get like maybe 50% more throughput. And the hardware they had to add to do this wasn't that much. So it's a pretty good trade-off if you've got lots of threads. If you don't have lots of threads, then it's wasted, but it's not that much hardware. Okay, so they're changing some, but they still have a heavy focus on single thread performance. That's still, core count has also become important, but single thread performance is very important as well. Their clock is high, 3 gigahertz approximately. In lab 2, you're going to do some comparisons of a computation on a CPU, a GPU, and an FPGA. So the UG machines that you're going to use have an Intel Core i7 processor in it, and this is just the statistics on that, so you can kind of bear that in mind in your comparison. They have 8 cores. They're 14 nanometer, so pretty recent manufacturing process. Their clock frequency is highly variable. So the clock frequency is 2.5 to 4.9 gigahertz. The reason why is it so variable? Like, if you go to buy a processor nowadays, like it's more complicated than it once was. Like when you're trying to figure out what is the clock frequency of this, you want to have fun, go to Best Buy, ask one of the salespeople what the clock frequency of a laptop is, okay? And then if you know a lot about that laptop, you can basically just tie that salesperson in knots, right? So why is it such a wide range? Yeah. Yeah, because these are power consumption constrained. So this processor can go up to 4.9 gigahertz, so its timing will permit that. It generally cranks its voltage up to make that happen. And if you're using only one core or maybe 2 cores, you can get that. If you're using all 8 cores, and especially if you start using this very wide SIMD, so you've done a great job as a programmer, you're getting lots of throughput, you do now lose some of your clock frequency. It's still a net win, but you're dissipating so much power. The processor is monitoring its power consumption, its heat dissipation. It'll throttle its clock back. It will also drop its voltage, because to run at 2.5 gigahertz, it doesn't need as high a voltage, which also helps its power consumption. Okay, so let's talk about GPUs. So again, you're going to be running on a GPU. We're going to give you basically the code for CPU and GPU. So I'm not going to make you just as a side project take a GPU course inside this course. Don't be worried. But we want to, it's an exercise in kind of seeing for yourself what are some of the performance comparisons on a computation. Did you have a question? Yeah. Yeah. There's 2 threads in the hardware on 1 core that it can execute in a single. It's not even. It's basically. It can actually be interleaving instructions from both of those in a single cycle. Okay. So because it's tagging them, so I actually have to change this. This isn't even quite right. It's it's basically tagging the 2 streams and actually just be able to send them both in at the same time. Some instructions from each. Now you have 8 cores, so you can have more threads than this. And then the operating system, let's say you make a program with 100 threads, the operating system will just time slice them. So you can use as many threads as you want. It's just that after you've gone past 16 threads on this particular machine, you won't get any more throughput because the operating system will just be putting that one to sleep for 100 milliseconds, having this one run. Okay, so it's perfectly fine as a programming construct, but it won't help you get more performance. But up to 16 threads on this machine will help you get performance. Does that make sense? Okay, so let's talk about GPUs. So the GPU and the UG machines, and you have to log into one of these ones. These GPUs are expensive, so they only put them in a subset of the UG machines. It's this particular one. It's an NVIDIA RTX 3070, which is based on NVIDIA's Ampere architecture. So NVIDIA gives every microarchitecture a name. So if you want to know more about how does this GPU work, you actually want to look up what's called the Ampere architecture. It's a pretty advanced GPU. So 8 nanometers is about as good as it gets. So notice this is like a process generation ahead of the CPU. So Amin is currently working out some process generation correction factors so you can do a fair comparison. One of the things you don't want to do when you compare devices is generally just have like a really recent GPU and an older CPU and compare them, because it's not a fair comparison. Okay? And in this case, the sysadmins bought some really high-end GPUs, but only a few of them. And then they bought more GPUs, but a little bit older. So we're going to give you some correction factors. What's in each of these GPUs? So each of these GPUs has 46 what NVIDIA calls streaming multiprocessors. So a streaming multiprocessor is essentially a core. Okay? It's the equivalent of one of those Intel cores. Each of those cores, so like a little processor, each of those cores has 4 32-way SIMD units. And that's what's kind of shown over here. This is that Ampere architecture. There are 4 of these SIMD units. I'm not going to go through the details of them because it is pretty complicated. But basically, NVIDIA calls every function unit, floating point function unit, a Cuda core. So there are 128 of these floating point pipelines per streaming multiprocessor. So essentially, each of these streaming multiprocessors is kind of like 128-way SIMD, but it's a little more flexible than that. They basically essentially can issue 4 instructions to 32-way SIMD. So it's a little more flexible than 128-way SIMD, a little bit less flexible than just having 4 instructions that are totally independent for 32-way SIMD. And if you want to work out the precise details of that, there's like an enormous amount of documentation you can try to wade through to try to figure out the exact details. They have explicitly managed scratchpad memories. So what they call this register file, which is big. It's like 16,000 registers for each one of these 32-way SIMD units. So that's a lot of registers, a lot more registers than a regular processor has. That's basically like a scratchpad memory. Like you organize, what am I going to fit in there? Okay. So whereas a processor has a much smaller number of registers and then kind of big caches to try to keep those registers fed, a GPU basically gives you a lot more registers and says it's your problem. Now they try to make that easier by having compilers that take your CUDA code and use these registers, but it's not fully hidden from the programmer. This is part of what a GPU programmer has to figure out how to do, how to use all these registers. And they're using all these registers to basically keep the threads busy, right? Thread does a little bit of work, it switches to another thread. Well, it switches to another set of registers. So that's kind of the challenge of GPU programming. In early GPUs, like you really had to work very hard to get all your data in these scratchpad memories and organize it well so that all the threads got the right memory and they never stalled. They've gradually added in some things that are a little more like a general purpose processor to make this less difficult. So they have this shared memory here. So all of these 4 streaming or 4 SIMD units can talk to this shared memory, which is 192 kilobytes. And they've got that for every streaming multiprocessor, so every core. You can either manage that yourself, like you decide what goes where. And in early GPUs, that was the only way to do it. The programmer had to control this. Now you can also ask the hardware to just use it as a cache, to just make programming easier, but probably a little bit less efficient. And then they also have an L2 cache, And actually, I got to go check this number. This 2 megabytes might be wrong because I didn't update that. But they have an L2 cache for the whole chip. And it's, again, to take some burden off the programmer. So it's taking a page from CPUs. So there's some convergence here, right? CPUs are putting more SIMD units in and a few threads. GPUs are putting some caches in to try to make programming a little easier. But there's still significant differences, right? GPUs go much further on SIMD still than CPUs do. They don't have out-of-order instructions, out-of-order instruction issue. Instead, they rely on having a lot of registers and a lot of threads. This is high power. Okay, so it's 220 watts, which for a GPU is considered kind of moderate power, right? GPUs take a lot of power. And its clock ranges from about 1.5 to 1.7 gigahertz, again, depending on what it's doing. The last thing it has here, which I'm not going to talk about, is Tensor Cores. Who knows what a Tensor Core is? Have you ever heard of this? Okay, so Tensor Cores are little matrix multiply units. Okay, and they're built using they're built using a data flow architecture, like a streaming architecture that's called a systolic array. So data kind of streams in all the time, and they're multiplying 2 little matrices. Usually, I haven't checked this generation, but the previous generation, it was like 4 by 4 matrices. It turns out that that's useful in a bunch of linear algebra. You can multiply big matrices by combining little matrices. And that's useful in linear algebra for scientific computing, and it's useful for deep learning. A lot of deep learning is about basically doing multiply, accumulate. So I'm not going to talk about this. If you want to learn more about it, take a GPU course. But they also have these kind of specialized units for small matrix multiplies that are quite useful for deep learning and matrix algebra. So that was like a 1-slide GPU architecture introduction. Any questions? And I'm going to have the caveat of any really hard ones I'm going to give to Amin, who can also just tell you the course code of the GPU course. So, okay. Okay, so we've covered 2 out of the 3 kinds of processors that people usually use. So last kind is Dsp processors. Dsp processors are optimized for signal processing. They have simpler control. They focus on loop processing. So in a way, they're not targeting single-thread performance, right, like a high-end processor would, but they target lower power targets than GPUs as well. They're optimized for multiply accumulate, because that's what you do in signal processing. And some of them are very low power. So this is a TI, in one of the labs here at U of T, we have these TI C5000 series DSPs, and they only take about 100 milliwatts. So they're really low power. You can put them in deeply embedded equipment. And for these ones, they basically have a little bit of on-chip RAMs, use Dma engines. So Dma engines are just little hardware units that go out to main memory and grab the data you want and move it on chip. And then basically the instructions execute from that on-chip memory and work with the on-chip data. And let's see, this one is targeted at integers. And for signal processing, 17, 18 bits is enough for things like wireless signal processing. So that's why they have these 17-bit integer units. They don't have 32-bit integer multiplies. And this particular chip uses a very complicated instruction set. So their instructions, they have instructions like this, like repeat, load with update, and multiply accumulate. So this basically encodes an entire loop. It says repeat over and over again, getting some data, multiplying it by some other data, storing it in the accumulator. So they do that. Basically, that turned out to be a pretty good idea for a low-end DSP that wants really low power consumption. It isn't a great idea if you want to go to higher performance, because it's difficult for a compiler to automatically make instructions like this, right? A human can hand tune it, but a compiler has trouble. Okay, so I guess I answered that. This was a hard compiler target. So TI also, so Texas Instruments also has a higher end series called the C6000 series. It's higher power, higher performance. It's a VLIW architecture. So the instruction words control multiple units. It's easier for a compiler to target this. It's easier for the hardware to decode the instructions and figure out what they mean, which can help it achieve higher performance. And it's got somewhat more parallelism. So basically, this series of DSPs basically has multiple units. So it has several load store units and 2 multipliers. And the multipliers can use a little bit of SIMD. So each multiplier can do 1 floating point operation, or you can partition the data path and do 2 16 by 16 multiplies. In order to basically reduce power, instead of having 1 big register file, they kind of partition the register file. So the 1/2 of the registers feed 1/2 of the compute units, the other half of the registers feed the other half of the compute units, and then I'll erase that. And then they have a few instructions that can move data between the register files. So that's a bit more inconvenient for the programmer, because you kind of have to remember, if you wrote this assembly code for this by hand, you have to remember these registers can feed these, this multiplier. These registers can feed this multiplier. But it's a way of getting less centralized state. In the first lecture, we talked about how in a processor, if you put everything in a register file, everything in a big shared memory, it's very easy to program, but big register files take a lot of power, a lot of area. So they partition it and tell the compiler about that, and it gets them somewhat better power efficiency. Okay? And then some later versions of this basically added SIMD instructions. So everybody likes SIMD instructions. They added basic instructions that could do 4 floating point multiplies instead of 1. Okay, I don't think I'm going to talk too much about the details of this. It basically has small caches, small L1, small L2 caches, and it's kind of like a GPU. So you can have it used as a cache where the hardware automatically decides what to put in it, just as you touch main memory, or the programmer can explicitly manage these. You can use them as scratchpad RAMs where you decide what goes in and when it comes out. That's useful for signal processing because, well, in signal processing, sometimes the programmer knows a lot. Like they know exactly the loop structure. And sometimes they care also about being very deterministic in the timing. It's not enough to run this fast on average. You must always run this fast because otherwise you might drop a cell phone call or you might not keep up with the data from the MRI machine or something. So in those cases, the fact that it can explicitly manage the cache, like decide what goes in and what goes out, can be useful. I don't want to talk about, there's basically a whole lot of variants of this, right? So you can get multiple cores of these DSP processors and so on. And they have a wide range of power. So they can be not as low power as the first DSP I showed you, which is like 100 milliwatts, but they can be from about 1 watt to about 20 watts. And if it's 20 watts, it's going to be like one of these multi-core versions that has, SIMD units and so on. So they've got some powerful ones, and they've got some ones that are much more less power, less computation. Okay, so to summarize, so DSPs, CPUs, and GPUs are all variations of processors. They have different power budgets. So a high-end CPU is usually around 100 watts. The ones in the UG machines are a little lower, about 65. GPUs are usually around 300. The ones in the UG machines are a little lower, about 220. For DSPs, the range is lower, from about 1 watt or less than 1 watt even to 20 watts. FPGAs also have a really wide range. This is historically about the range of FPGA power as well. Little FPGA would be less than 1 watt, big one would be 20. For the latest FPGAs, like 14 nanometer and higher, the power budgets have been creeping up. So for those FPGAs, if you buy a big one, your power budget can easily be 60 or even 100 watts. So it can get into the range of a CPU, although I've never seen an FPGA approach that, like 300 watts. So there's some convergence. DSPs and GPUs have started sacrificing some die size to make programming a bit easier, to have caches, for GPUs to put in floating point, or for DSPs to put in floating point units. And at the same time, processors are leveraging SIMD and multi-threading more. So there's some convergence, but they're still somewhat different. So DSPs use a little bit of SIMD, processors more, while high-end processor more, and GPUs the most. Okay? There's also some divergence. So CPUs spend a lot of area trying to make single-thread performance fast, whereas GPUs don't care nearly as much about that. GPUs have are instead built to be latency tolerant, that they have lots of threads and they're just switching between them rather than trying to make one thread run fast. And DSPs basically rely on the programmer telling them more. What is the exact schedule? When exactly should this data come into this this scratch pad memory, and when should it move out in order to stay busy and get good power efficiency? Okay, FPGAs kind of rely even more on custom stuff. You have to explicitly schedule the data movement yourself. You can create a custom memory subsystem that's highly distributed, create a custom memory processing pipeline. They're best at small data types, right? So because it doesn't take very many of those LEs or DSP blocks, and they're pretty good at integers. They have been weaker at floating point, because if you build floating point out of just DSP blocks and logic elements, it takes a lot of logic elements. But recent FPGAs, from the one you're using in the labs, ARIA 10 and beyond, have actually added DSP blocks that could directly do floating point. So that's made FPGAs a lot more efficient at floating point. Not more efficient than certainly a GPU, but more competitive. And FPGAs are the only platform that doesn't need an instruction stream. So you can put soft processors in them, but you don't have to. Everything else is some kind of processor, just making different trade-offs. Okay, and I'm going to pause there for 10 minutes. So we'll come back at 5:39. That's the lead into this first paper, which kind of did a peak analysis of various kinds of devices, of what are guaranteed not to exceed numbers that try to capture some of the compute differences between them. Okay, actually I just pushed you to 5:40, so now you got till 5:40. Come back then. Okay.
You're still getting. Are you okay?
Yeah, it's
Weird.
yeah.
My light on here it doesn't go on.
but it is a guarantee that you won't get any more than this. This paper, yeah, what this paper did is it's trying to do max performance comparisons across a wide range of devices. The danger in that, obviously, is you can't really hit the peak performance usually in most applications. But at the same time, I think there is some value to this paper because it's also really hard to compare across a whole bunch of devices with a bunch of applications, because every application takes a lot of work to put on each kind of device and to fully optimize. So it is very difficult to say I'm going to take like 15 applications, try them on 20 devices. I mean, this might be like a 200-year PhD, right? Which is not feasible, right? The department won't let you do that. So, so a peak performance analysis is much easier to do, but you have to put caveats on it of we're probably not going to achieve the peak. So we can just use it as kind of informative. So that's what this paper sets out to do. Take a whole bunch of widely varying devices and just find their absolute limits. So they compute a few different things. They compute something they call computational density. So how much compute can I get done on each one of these devices? Computational density per watt. And then those are both about on-chip computation. If I have all my data on chip, how much compute can I do? And then they also ask, well, how much off-chip memory bandwidth do I have? I mean, they take into account on-chip memory bandwidth when they're calculating these two numbers. They then also want to look at how much off-chip memory bandwidth do I have to see can I get all my data in and out if I got a big data set. Does that make sense? So, because before I go any further, how many people read this paper? How many chose this as one of those ones they're doing? Okay, 2. All right, is that it? Only. Oh man. What do you think? Any thoughts on it? Where you go, this is like I loved it, or this is like the worst methodology ever. What do you think? Or maybe you're in between. No strong opinion? Just like I read it? Yeah.
So I have a question. So,
Yeah.
Can you explain more about the computational density, like the computation per
Well, yeah, so I'll show you that in a minute. So computational density is essentially how much computation on chip can each of these devices do. And they just call that computational density. I don't know why they call it computational density versus just computation, because there's no divide by mass or anything, like divide by weight. Okay, so I'm going to take that as no one has a strong opinion on this paper. Okay, so I'm going to keep going then. Okay, so I guess the first thing that they want to compute is just how much on-chip compute do I have in a processor versus an FPGA versus a GPU versus a DSP. Okay, what can I get done? And they focus on, well, they do both integer and floating point. So let's just focus on what they do for integers. So for the processor and the GPU and the DSP, they just say how many compute units they have, how many integer computations can they do in parallel, what's the clock frequency, and then they check, can I get that much data to them? Okay, so if on the processor they check, can the first level cache get that much data to the integer units? Because if it can't, they say, well, it's going to be throttled by that. So they're basically assuming the data is on chip. For the processor, they say it's L1 cache has to provide the data. For the GPU, they say, okay, can the register files, which are very large on a GPU, can it provide the data? And it can, right? Like in a GPU, it would be kind of crazy to build more integer units than the register file could feed. They do the same check for a DSP. For an FPGA, it's a bit more tricky because you can build anything, right? So on all the other devices, they're just checking, can the register file, or in the case of the CPU, the L1 cache, keep that many integer units fed? And if it can, they say, fine. The number is just integer units times clock cycles. But for the FPGA, how many integer units do we get, right? You can't point at an FPGA and say. You have to actually make a design to see how many integer units you can fit on it. In order to determine can you keep all of those fed from memory, you have to decide what memory system did I build? Because you don't have a register file on an FPGA, you don't have an L1 cache. You just have a whole bunch of block RAMs. So they have to make some decisions on the FPGA of what's a reasonable benchmark for integer performance. So what they do is they say, well, we're going to build one multiply and one add unit, because on the DSP, the GPU, the processor, that's what they're doing. They're saying an integer add plus an integer multiply. So a multiply accumulate. That's the basic operation. So we're going to build that on the FPGA. They have to figure out how fast it can be clocked, right? On the CPU and DSP, You just look it up. On the FPGA, you have to run through the CAD tools, and they tell you what your maximum frequency is. So they measure the frequency, and they do that with just one unit. So kind of like what you're doing with Lab 1. And that one unit, they basically feed each input of that multiply accumulate unit. So they're going to take two operands in, multiply them together, and then add it to a running total. So they basically say, well, we'll say one block RAM is going to feed one of those two inputs, and another block RAM is going to feed the other input. So they can fit, on a typical FPGA, it means maybe they could have 1,000 numbers in each of those block RAMs. And they say that seems pretty good, right? There's a bunch of numbers that are in there, so that seems like a reasonable memory system. Does that make sense? So they've got a multiply, followed by an accumulate, and they basically have one RAM feeding one input and another RAM feeding the other input. So that is their basic compute unit. They pipeline this, because not pipelining it would be silly. In an FPGA, you should pipeline this deeply, so they stick pipeline registers in there wherever they think it's appropriate. And they measure the frequency of this whole block. And they, based on these resource counts, so they use 2 block RAMs, they used a DSP block, they use some logic. What limits how many they can fit on the chip? They say, I get that many units at a certain frequency. Does that make sense? And they basically replicate until the device is 85% full. So they don't go to 100% full because they say, well, you're going to need some control logic, and we didn't build any control logic. We didn't build any data path to get data from main memory, from off-chip memory into these programs. So there's going to have to be something else. We're not going to build that, but there'll be something else. So we'll leave 15% for that. So for example, they take a particular Xilinx device, and when they're doing 32-bit integer operations, they find that they can fit this many multipliers and adders. 968 multipliers and 969 adders. So they're going to have to round that. They're going to say they're limited by the multipliers. So 968 units. They check, do I have enough RAM? And they find, yeah, I have enough block RAMs that I could feed 1,064 operand pairs. So I'm not limited by the RAM. I'm going to be limited by the multipliers. That's my lowest number. That's how many units I get. They measure the frequency for one unit. They get 296 megahertz. So they basically take 968, multiply it by that frequency, and say that's how many billions of operations per second they get for this particular device doing 32-bit integer operations. Okay, and let me erase all the scribbles. Hopefully that's clear. Does that make sense? So pretty basic compute unit. They do check that they can feed it with some reasonable amount of data. What do you think of this methodology? Seem good? Seem bad? You think it's optimistic? You think it's pessimistic? What do you think? Yeah.
It's definitely not accurate. Because first 15% here with that. How do you get this number?
So they just made it up. They basically said, we think that we can do mostly data path for the typical application, and that there's going to be some control logic and some space to get the data from off chip. And we think that's going to be 15%. So that's the argument. So it is not extremely detailed. So.
Yeah, and also when you pack the device to nearly full, you have lots of congestion, and the clock frequency will be low.
Yeah, okay, so it's a good point too. Okay, so you're basically, let me repeat that in case people can't hear it all. So you're questioning, where does 15% come from? And it's basically based on their experience. It's going to vary a lot from application to application. So clearly there's a pretty big margin of error on that. And then you also pointed out something important, that as you fill an FPGA up, the clock frequency does tend to drop for two reasons. You can get routing congestion. So there's just some problem getting the exact wiring you want. So you built one unit, and these RAM blocks and this multiplier and this adder, they all got exactly the routing they wanted because they're the only thing in the chip. And they all got put right beside each other. It's a very happy nuclear family, right? But then as we stick nearly 1,000 of them in the chip, I mean, this is now like some kind of encampment. This is like Woodstock. There's some competition for routing. It's no longer this happy family. Also, there's more room for the CAD tools to screw up. It's just, even though there should be a solution that is just as fast, if you could just replicate that previous one, it might not be possible. You might start having to fit things in the corners, and they might not be able to use the nice same placement. Also, there's just more room for the CAD tools to screw up, right? You got 1,000 things to do instead of one. And if one of them is poorly placed, meaning you get some long interconnect paths, your frequency drops. The FPGA CAD tools usually do a reasonable job, but it means that there's going to be some pressure on this clock frequency. You know, it's not going to get faster as you replicate it, and it's probably going to get at least somewhat slower. So yeah, their methodology is probably a bit optimistic for an FPGA, because this 15% might be low. You know, it might be high too, but 15% is not that big a number, so it's more likely to be low. And they're kind of neglecting that they will get some clock frequency drop as they fill the device. It's probably not wildly off though, right? So you know, you can say maybe you drop their numbers by 20%. You probably don't have to drop them by like 10x. Does that make sense? And also what they're comparing to is the CPUs and GPUs with basically all the data in the register file of L1 cache, which is also quite optimistic. You know, you usually do not manage to fit all your data in the GPU register file and never have stalls, or you're always in the L1 cache and you never get stalls in the CPU. So in that sense, it's probably in line with what they're doing for other devices. Okay, so what are the results? Okay, so they basically take CPUs, and they range from Atom, which was a low-power x86 processor, to a couple of higher-end x86 processors. Many-core. So many-core is basically, these are Intel devices. Xeon Phi is a series of processors from Intel that are targeted primarily at supercomputers. So they use that AVX 512, really wide SIMD, simpler cores, more of them. So it's intended to be an x86 processor that is targeted at essentially throughput computing. Like, give me more cores that are a bit slower to compete with GPUs and supercomputers. Probably not the processor you want to put in your laptop, but that's its target. Then we have some DSPs, so the ones that we just talked about, and then a bunch of GPUs. Okay, so this paper was done a few years ago, so all of these devices are a little bit like they're not the latest devices, but they're all basically at the same. They're similar process generations, so they're actually comparable to each other, which is more important than being kind of the latest. And then these last ones are kind of devices that kind of mix a couple things. Like these are DSPs that also have a processor for control logic. So anyway, this is showing how many gigaops we can get from various devices. And it's versus operand width. So int16, int32, single precision or 32-bit floating point, and double precision or 64-bit floating point. So I guess what do we see? Let's take this Opteron. This is the best performing x86 processor, so high-end processor. It does much better on int16 than int32, and then does better on integer than it does on floating point, and even worse on double precision floating point. Why do you think it's dropping as we go from int16 to int32? What would be the reason for that? It's like a test of comprehension of what I talked about earlier. So why would I get more int16 operations on a processor than 32? Yeah?
I would guess it's using, you can either operate like one 32-bit instruction or the same hardware using two 16-bit instructions.
Yeah, that's exactly it. So it's the SIMD width gets wider. If you look at the list of SIMD operations for, this is an AMD processor, but it's pretty much the same for other processors. They basically make a certain width of data path for SIMD instructions, and then if you use narrower operands, you get more operations. So this, I can't remember the details of this exact processor, but let's say it would probably do 4 32-bit operations in SIMD instructions, or 8 16-bit. So you see there's basically a 2x advantage of doing 16-bit operations. Why can they do more integer than floating point? Probably they built more integer units. That would be my guess. And then if we go into these many-core devices, which are targeted more at supercomputers, you see they basically focus their SIMD operations on single precision floating point. So that's why the kind of single precision floating point is the same as everything else. They just didn't bother to make 16-bit integer, et cetera, get more throughput in the SIMD units. DSPs have much lower performance, and it's hard to see maybe, but they have the same trend of 16-bit integer as they're happier with that for the same reason, get more operations per SIMD unit. When you get to the GPUs are optimized for 32-bit floating point. So they get really high 32-bit floating point. They don't actually benefit much from the other things. These GPUs are a few years old. If you did this again on a very recent GPU, 16-bit operands, they will usually get higher performance on because they now split the data path for 16-bit operands. And the reason is for machine learning. For graphics, they really wanted single precision floating points. They didn't really care very much about things like 16-bit integer or weird 16-bit floating point operations. Deep learning is all about multiply accumulate performance, and it can be done at lower precision. So the most recent DSPs would have essentially this trend. They would get higher performance with 16-bit operations than with 32. But I guess the key takeaway here is for just raw floating point performance, the GPUs are really good. For integer, they're not bad, but some of the CPUs are competitive. OK, so this is the result for FPGAs. And for FPGAs, we see int16 for basically everybody is always higher than int32, which is higher than floating point, and so on. Why do you think that is? So in an FPGA, why is that? We didn't explicitly build SIMD units. Yeah? Yeah, so that's exactly right. So if you build a 16-bit multiplier, we're going to actually see how to build these a little later because we'll look at the DSP blocks. But basically, the amount of logic you need to build a multiplier grows with the square of the multiplier width, OK? And you'll see that later in the course. We'll actually go through that in a little more detail. So basically, FPGAs can build a lot more small operands than they can big ones because it doesn't take as much logic. It also doesn't take as many DSP blocks, but that might be less obvious until we look at their architecture. So that's why they do better with 16-bit integer than 32-bit, and they do a lot better. It's actually more than 2x. So it's a bigger difference than it was for the processors because we're basically building these multipliers out of DSP blocks and logic elements, and it's more like a square than a linear change when you go to a bigger multiplier. The other thing is we lose some more when we go to floating point, and for at least most of these. So most of these have lower results for floating point. And it's because floating point takes some additional logic. You have this exponent that is moving around and making you shift your number. Shifters actually take a fair amount of logic. So floating point takes more hardware when you're actually building it out of the programmable fabric than integer does. Does that make sense? So small precisions, friendly for FPGAs. Floating point, not as friendly. OK, that was compute. And yeah, it's probably hard for you to remember these because they're not on the same axes, but I have a few numbers later. Yeah? Yeah. One more?
Yeah, for this one, I don't think it specify like how many like FPGA resources are used to build a floating point.
So what they do is they build one floating point multiply accumulate unit. They see how big it is, like how much logic, DSP, et cetera, it takes, and then they figure out how many they can fit on the chip. So basically, as they go to a floating point unit, they can't fit as many on the chip, which is why the bar goes down. Their throughput number goes down. Does that make sense? So it's not like they compute it. They basically implement one, get the resource counts, compute how many could fit.
Yeah, I'm just curious why it doesn't specify.
Why didn't they put those numbers in?
Yeah.
Yeah, it's a good question. I mean, maybe they should put them in. So it's a good thought. That would give you a little more insight into how they got the numbers. OK, so that was compute density. They also could do compute density per watt. So for the fixed function devices, they use the a GPU, CPU, a DSP, when you buy it, it comes with a number called the maximum thermal power dissipation that you use to figure out how big a heat sink to put on it and whether you need a fan and so on. So they use that number, right? This will not use more than this much power. Let's use that number. And they just divide how much compute they get by that number. For FPGAs, it's a little more complicated because an FPGA, how much power it takes depends on what you put in it. Like not just how fast you clock it, but also what kind of design did you put in it. So the basic equations for power is your total power is dynamic plus static. Static is easy, okay? Well, it's easy for an end user, okay, because it's just a spec of the device. This chip leaks this much current. It's because you can't turn the transistors fully off anymore. So when you add up 10 billion transistors times a little bit of leakage, it turns into a reasonable amount of power. But you just get a spec. Static power strongly depends on temperature. Transistors leak a lot more as they get hot. That's all included in the spec. They'll give it to you at a certain temperature. You take the highest temperature that you're ever going to use this at. If you know you're going to use it at a lower temperature, your static power won't be as big. The dynamic power is harder because it depends on what are you doing. So this is the basic equation for dynamic power in a CMOS device, which is what all modern chips are built from. So it's basically charging and discharging capacitance. That's what's dynamic power. So this equation is actually pretty easy to work out if you remember your first year electrical fundamentals. So the energy to charge a capacitor is 1/2 CV squared. Okay, so this is just the device voltage. This is the total capacitance that you are charging and discharging, well, that you are charging every cycle. Okay, and the total capacitance is basically add all the capacitance up that is changing, like that has signals changing, which you kind of have to get from the device manufacturer. You don't know that, but that's some number for that chip. And how often you're charging and discharging it is once per clock frequency. So clock edge happens, and now things start changing. So you start charging and discharging the capacitances inside your circuit. But you don't usually charge and discharge every single gate. So this alpha is how much of your logic is changing state in any one cycle. Does that make sense? So if your chip is not doing much, right? Like you're not sending it any data and none of your registers are actually changing state, this alpha is very low because nobody's changing anything. If you are changing the inputs and all of the downstream logic changes every time you get a new input, then your alpha is high, okay? So this alpha is between 0 and 1, okay? Typically, it actually can go higher than 1. The way it goes higher than 1 is if you actually have some gate that changes a bunch of times in a clock cycle, which can actually happen. It's called glitching, where basically it's the inputs of that gate change multiple times in a clock cycle and its output changes multiple times per clock cycle. It's wasteful. You generally don't like it. But it does happen in things like XOR gates, where any change, you got a 3-input XOR and all the inputs change at different times every clock cycle. That output of that XOR will actually change multiple times per clock cycle. So, so usually it's less than 1, but technically it can be even higher. This is actually the hardest part to estimate, right? This alpha. And in lab 1, you're getting this toggle rate. The toggle rate is actually the frequency times alpha. And that's actually reported to you by that simulation you're doing, and you're getting the toggle rate per block. So that's actually the most accurate way to get it, because people usually don't know how often is my logic toggling. The FPGA CAD tools actually know the voltage. They can work out all the capacitance because they know the place and route. But this, and you know the frequency, but this alpha has to come from simulation. Okay, so does that make sense? That's how you do power estimation. The device is 85% full, so it's pretty full. They take the maximum frequency reported by the CAD tool, which makes sense because they use that same maximum frequency to get how much compute. They assume alpha is 100%. So alpha equals 1 for them, which means that means every single gate in the design changes every single cycle, or the average lookup table, RAM output, routing wire, etc., that's used by the design changes every single cycle from either a 0 to a 1 or from a 1 to a 0. So what do you think? Does this seem realistic? Yeah. Yeah, so the comment is that this toggle rate seems very pessimistic, and it is very pessimistic, okay? So 100%, even if you have, let's say that I have a RAM block, okay? Well, let's just not do a RAM block. Let's do a lookup table, and let's say I put registers on its inputs, so the inputs change once per clock cycle, and you're trying to figure out how often does the output change. So if I randomly change the inputs of a lookup table, the output used to be 0, it's about 50% chance that the output's still 0, okay, on average, and about a 50% chance that the output becomes 1. So even if I'm randomly changing the inputs to my logic, you only get 50% toggling. Does that make sense? So it's theoretically possible to get 100% toggling. Like I said, you can have a gate that changes multiple times a cycle, but it is not common. Even random changes are typically 50%. Usually in a design, you actually get less than 50% because you have things like finite state machines, you have parts of your data path that might not be active, you have some correlation in your input data. There are a bunch of reasons why usually the toggle rate's less than 50%. Now, what they're doing where they're just saying we're taking a whole bunch of numbers from RAMs and sending them to multiply accumulate could be 50%. Because you could say, well, every cycle, every compute unit gets new data. The new data has nothing in common with the old data because we're just doing a little kernel. So 50% is probably defensible here, but 100 is very pessimistic. And in real designs, because of all the things I just talked about, finite state machines tend to not change all the logic from one cycle to the next. Parts of your data path, the way people build data paths, they often have a lot of muxing. So they're kind of like select this or select that, and the part that's not selected doesn't change. So a more typical number is, maybe 15 to 25% is a more typical toggle rate. Although if you're just doing multiply accumulate, then you could certainly be 50%, because just doing a whole bunch of multiply accumulates could be that. But I would say their power numbers for the FPGA are pretty pessimistic because of this 100%. Does that make sense? Their power numbers might be slightly, well, what about for the other devices? So they're using the maximum thermal power. Is that pessimistic for the other devices? What do you think? Yeah, it might be a little bit, although I don't think it's too bad, because if you actually take those, you take a GPU and you just say do floating, all your register files got all the data for you. You're just doing flat out floating point operations. With all your cores, you are keeping every single piece of it busy. There may even be a bit of optimism of it won't go beyond this thermal dissipation spec, but it will drop its clock frequency. For GPUs, they drop their clock frequency a little. You saw for the CPU. The CPU we're using in the lab has a clock frequency from 2.5 to 4.9 gigahertz. So it can actually be a significant thing that in order to avoid going over that power spec, they're dropping the frequency a lot. Yeah? Yeah. So you're saying they could have put it in the chips and actually measured it. Yeah, that probably would have been a better methodology. So I think on power, they're a bit pessimistic for the FPGA for a couple of reasons. The biggest one being this 100%. OK, so what do they get, though, for power? I mean, to be honest, the most important thing probably nowadays is compute per power, because you can buy more boards, you can buy a bigger chip. So probably even more important than compute performance nowadays is how much compute per watt. So what do they get? These are the processors, okay? They prefer int16. They're more power efficient. That kind of makes sense. They get more SIMD like we talked about. Xeon Phi is really targeted at getting high throughput. Clearly has a fairly big power usage, so it's actually not as good for power efficiency. The DSPs were pretty bad for raw throughput, but are actually pretty good for power efficiency, so throughput per watt. And the GPUs are, kind of in the middle. They're actually not, they're pretty good for floating point in terms of compute efficiency. They're not as good for integer. And actually, these are hybrid devices that are basically DSPs. And those are the best of all, right, in terms of power efficiency. Okay, these are the FPGAs. Kind of shows the same trend. 16-bit, much more power efficient than 32-bit, more power efficient than floating points, and so on. Let's see. The other thing you can see is this is a 40 nanometer FPGA, and this is a 28 nanometer FPGA. This is 40. This is 28. So generally, the smaller process nodes have higher power efficiency. So this 28 nanometer Xilinx FPGA has significantly better power efficiency than a chip that's pretty similar, but at 40 nanometers. So does that make sense to you? Should power be going down as you go to lower process nodes? What do you think? Okay, so see you're nodding your head, and you're right. Yeah, why does it go down? The reason I bring that up is a lot of people have been, they're so worried about static power, they think that power goes up as you go down process nodes. So why do you think it should go down? Yeah. Yeah, so that's exactly right. So the capacitance goes down as you go to a new process node. Your wires get shorter. Your transistors, their area gets smaller. The wires also get closer together, but when you actually work out all of the basic physics of it, your capacitance goes down somewhere between linearly and quadratically as you scale. Okay, so you scale the process down by 70%, your capacitance is going to drop somewhere between 30% and 50%. Transistor capacitance drops more like 50, the wire more like 30. So that's good. You also get a little bit of a drop usually in voltage. Less than we once got because we can't drop the voltage as aggressively as we used to because we're getting just too close to the threshold voltage. And as you approach the threshold voltage, just your transistors are like no longer turning on and off. But we're still able to drop the voltage some, which also it reduces power. Now, the reason some people think that power goes up as you go to a lower process node is who's heard that static power is a bigger problem than it used to be? Nobody? Okay, maybe this is there was a period like for some years where it was like the industry was panicking about static power. You saw article after article showing, plots showing static power going up, and by this point, like we'd have chips. This chip would be basically irradiating me, and it would be like a Raiders of the Lost Ark kind of situation. But that didn't happen. What actually happens is static power transistors are getting leakier. Okay, the natural processing of them as they shrink and we drop the threshold voltages, they do leak more. But basically, process engineers and chip architects have to take mitigation measures to bring the leakage back under control every generation. If they just took the previous design and scaled it naively, static power would get out of control. They don't do that. Okay, they will basically do a variety of circuit and architecture tweaks until the static power basically doesn't change. From one generation to the next, it's about the same. You sacrifice performance in order to do that, but the static power for an FPGA usually is about 30% of the total power. Okay? And that isn't really changing much. And it's not changing much because that's what the FPGA architects want to do. They could make it even less than that, but in order to make it even less than that, they'd have to do things like increase the voltage, which would increase dynamic power. So this is kind of the sweet spot. So the static power is, after a whole pile of work, about constant, and the dynamic power drops, so you get an improvement. Well, the dynamic energy drops. You get more computation per unit of power energy. Does that make sense? Okay, so comparison. So I didn't have these on the same slide, so it's hard to tell. But the FPGA on 16-bit integer ops was about 10 times more power efficient than the GPU and about 5 times more power efficient than the CPU. We got best results for the most aggressive process node. So power per operation drops with process shrinks. And again, it takes a lot of effort by the process engineers and the architects to make this happen, but it makes sense that this is what's happening because does anybody know how much a new fab costs, like TSMC? I don't actually know what the last one cost them. I know what a generation or two ago cost them. So the last fab I checked the price of from TSMC was $9 billion US. So you don't build something for $9 billion that is state-of-the-art for only 2 to 3 years if it's going to make worse chips than the previous generation. Like no one with $9 billion is that reckless, okay? So yeah, you do get improvements with process shrinks. It's getting harder, but you still get improvements. Okay, floating point. So integers, FPGAs, very power efficient, especially low precision integers. So 16-bit integers, very good. Floating point, the FPGA in terms of gigaops per watt was about the same as the GPU, but it got lower throughput per device. So if you just want raw throughput, the GPU was best. For power efficiency, it was kind of a draw. Let's see. Because we already talked about this, some of the caveats of comparison. Like both of these are peak numbers. So I think you have to just take, these are only broad guidelines, right? GPUs don't usually achieve their peak, but we also talked about how the FPGA may not achieve its peak either. These FPGAs were like 40 and 28 nanometers. In the next generation, 22 nanometers, ARIA 10 put hard floating point units in. So instead of having to build the floating point units out of a mix of DSP blocks and logic, that's what had to be done in this study. The next generation just made the DSP blocks could do floating point essentially completely with dedicated logic inside of them, which made them more efficient. And that basically has made them more competitive with GPUs on floating point. I can't give you any really hard numbers on that. You have to check an application. But it used to be that you really wanted to avoid floating points in an FPGA. And now there are still benefits if you can avoid it, but it's not too bad if you need it. OK, that was all about the on-chip compute. This is what happens when they compare off-chip bandwidth. So the lighter portion, these are all those different devices. So the lighter portion is memory interfaces. So talking to DDR or GPUs often use something called graphics DDR, sort of a form of DDR that is essentially gives tighter timing specs and you can run faster. So all of the light part is basically talking to memory, like DDR. And then the dark part is everything else. So talking to PCI Express or Ethernet, any other thing. So what we can see is that the GPUs have, by far the highest memory bandwidth and a lot more than the high-end CPUs. These many core architectures that Intel is targeting at supercomputers were kind of in between. Okay, and this is for FPGAs. Okay, so what we see for FPGAs is the dark part is much bigger than the light part. Okay, so dark part is how much bandwidth to DDR, off-chip memory, and the blue part, dark part, is everything else: Ethernet, PCI Express, and so on. And basically, the latest FPGA chips have faster I/O, so they get the most bandwidth. Okay, so external memory bandwidth, like talking to DDR. So external memory, the GPUs have about 3 times what an FPGA has. But FPGAs have about 10 times more network or other I/O bandwidth. So why do you think this is? So, and part of it is the way they did their study. So in their FPGAs can actually build a lot of memory interfaces if you take most of the I/Os on the chip and you just say, I'm going to turn them, I'm going to make them talk to DDR. In this study, they basically, I have to go back and look at the exact details, but they only did 1 or 2 banks of DDR. But a typical big FPGA could actually talk to about 6 different DDR channels. So they could take these same chips, and if they made their own board, they could make them have higher bandwidth to memory. So part of it is, but they are also correct that most of the accelerator boards, you just go buy a board that somebody else made, they usually only hook up a couple of DDR channels to the FPGA. So that's kind of a decision that board manufacturers make, whereas GPUs hook every pin they possibly can up to graphics DDR. So I guess part of this is the FPGA, if you choose to, at the board design time, you can increase this external memory bandwidth. So yeah, any other thoughts on this? Not that many people have read the paper. It might be hard for you to weigh in. So I guess one of the caveats I just gave you, the FPGA could up this. Why do you think FPGAs have more network and other I/O bandwidth? Like so PCI Express, Ethernet, et cetera. Yeah. Yeah, so they're basically designed to have highly configurable I/Os, and a lot of their markets are communications focused. So the underlying chips that they're talking to, right? So an FPGA or a GPU, they are talking to the same thing. So you could make a GPU with as much Ethernet bandwidth as an FPGA, you can make your FPGA have as much memory bandwidth as the GPU. But the typical use case for the FPGA is I want a lot of Ethernet bandwidth, et cetera, so their IOs can do that. You can get more memory bandwidth if you want, but you just have to buy a board with that. So they're each kind of optimized for their use case. GPUs really focus on external memory bandwidth. FPGAs more on everything else. Okay, so let's see. Any questions on that? So it's kind of like a peak analysis. Hopefully gives some insight of where you might win, where you might lose. It's not, but your application, often you only get a small fraction of peak performance. So this is not like this is like a good calculation to do, because if you find that the peak numbers you would ever get are not a sufficient win for you to bother writing something, then don't do that. But obviously you're not guaranteed to get anywhere near the peak either. So it's just kind of a bound you check before you start optimizing. Does that make sense? Yeah.
For this paper, like, can you get some any like useful conclusion about which one, like which type of like processing using like a CPU or GPU is better than?
Yeah, it's not as definitive as that. Because if they came out with a conclusion saying everybody should use GPUs and CPUs and FPGAs no longer exist, probably that conclusion would be too broad, right? They do, I guess, quantify the, they clearly show 16-bit is better in FPGAs than it is in other devices. At this generation at least, GPUs were not that good at that. Single precision floating point, GPUs are really good at if you can keep the compute units fed, and so on. Does that make sense? So you could make some conclusions about what were promising devices. Real applications tend to be a lot more complicated, so they can't make a statement of, you should for sure use this. But let's say your application was a big matrix multiply, where it's known, there are ways known for big matrix multiplies to keep the compute units on a GPU fed. And let's say you could do it in single precision floating point. Well, then single precision floating point was both the most energy efficient and the highest throughput on a GPU, so you should use it. Does that make sense? Now, this generation of GPU, and current GPUs as well, are not as good at double precision. And a lot of in scientific computing, you actually need double precision numbers to do big matrix multiplications and other matrix ops. So you could use these graphs to decide, is the GPU a good idea for that? Or given that I need double precision, maybe a CPU is better. Or maybe my FPGAs are not very good at double precision, so I wouldn't do them. Their numbers were pretty low. Does that make sense? So it can give you kind of guidance like that. If I have a complicated, irregular application where I'm not 100% sure how I'm going to keep my compute units fed, then it's going to be much more difficult to analyze. You also could get answers like, this computation is mostly going to be about how fast you can get data from external memory, right? I'm going to always be waiting for external memory because of the structure of the computation. It's mostly memory transfer and then a little bit of data computation. In that case, a GPU has the best numbers for memory bandwidth, and you should use it. Does that make sense? So that's kind of where you can gain insight. The compute units on the FPGA are fairly simple, right? Block RAMs feeding a multiply accumulate unit. What you'd like to do in an FPGA is actually build a pipeline. So you'd really rather have like this compute unit directly feeding this compute unit, directly feeding that compute unit, and only like accessing RAMs maybe at the very input. If you can do that, you could actually get significantly better efficiency than what they said. So that's where you get into, the more complexities of your application. But there are classes of applications where these numbers will tell you what to do. Does that make sense? Like you would hate to basically spend 2 years in your graduate degree optimizing some design, and at the very end you figure out, this is all about memory bandwidth, and I did it on exactly the wrong device. And that's your future work. The next student should basically, the first decision I made, which was to target this device, you should actually make the opposite decision, right? It's a truthful future work, but it's sort of like it's kind of painful to write that. So, okay, so let me give you, I'm going to spend the last few minutes starting on the next thing. Summary of efficiency of these programming models. So this is an interesting paper that tried to figure out what the programmability cost of an FPGA is. So an ASIC makes gates and wires, and FPGA makes lookup tables and programmable routing. What's the cost of that? Okay, and the cost is pretty big. So if you're only using soft logic So just the LEs and logic blocks and the programmable routing. They took a bunch of designs. These designs are pretty small, so that's one caveat, but they found the average area gap versus an ASIC was big. It's about 35 times bigger. So that's large. And speed gap, whoops, that's the area gap. Okay, I guess the way order I did it in is this. If you use the hard blocks, though, it helps. Okay, so programmable logic and the programmable routing are kind of the least efficient part of an FPGA. They're essential, but they're like the least efficient versus an ASIC. So when you take a memory, a multiplier, they're a lot more efficient because the inside of them looks like an ASIC. They're just transistors. They have to connect to the programmable routing, so they do get programmable routing wires and muxes. That reduces their efficiency, but they're closer. So for the circuits that were used in this study, hard blocks improved things, but the gap was still 20x. Okay? But the circuits that they used were actually still very small and had very few hard blocks. So they were kind of older, too small. So they narrowed the gap, but not that much. But they're also probably not that realistic. So for example, they only had a few circuits that used memory. Plus, well, they had a few circuits that used logic and multipliers and a few that used RAM. How many large designs or modern designs do you think do not use any on-chip RAM in an FPGA? What fraction? Just take a wild guess. So it's between 0 and 100. What fraction of large designs do you think don't use any RAM on the FPGA? 0, right? So this is kind of a flag that, you know, these designs are probably too small and too old to be completely realistic because they only had 3 designs that used memory. So these are like old building block designs. So anyway, the designs that used hard logic closed the gap some, but not that much. The last case they did, this was actually done by Professor Rose and one of his students here. And while I kind of liked the work, I sort of abused him roundly when he presented this based on not having designs that were big enough. So he did another analysis where he said, fine, what if we assume that you use all the hard blocks? Which is not crazy. Like actually when you have designers fitting things in an FPGA, they look at what's available and they try to use it. So it is kind of it's a bound on how well you could do. But you basically say, I'm just going to use all the hard blocks on the FPGA and all the soft logic. What would I get? In that case, the area gap drops to 4x on the particular generation of FPGAs they looked at. And this is like a number that you won't do better than, okay? But it's not crazy, because this is how they actually do try to use what's there. Now, one other thing this doesn't account for is IOs. This is all about the core. A lot of what you're buying with an FPGA is IOs. The IOs are programmable, so they are somewhat bigger than an FPGA, but they're nowhere near 4 times bigger. So when you look at a system level, the gap is probably less than 4x still. But still, these are reasonably big numbers, right? So useful to know about. What about the delay gap? So the delay gap doesn't vary as much. If they take designs that are all logic, there's a significant gap. The ASIC can run 3 times faster. When they put in hard blocks, it doesn't change much. Okay, so the delay gap is 3.5x for things that have logic and multipliers, and 3x for things that have logic, multipliers, and RAM. Now again, these are kind of the only circuits that are, modern circuits have all these things typically. Why do you think the delay gap didn't change as much as the area gap? So area gap, hard blocks made a big difference. Use a lot of hard blocks, you're down to 4x. Use no hard blocks, 35x. Delay didn't really matter. It's about 3x no matter what. Why do you think that's the case? Is it just wrong? Should I go abuse Professor Rose some about this? Maybe I get some of you to go by and abuse him. Just don't tell him I sent you. Or do you think it makes perfect sense?
Maybe the major portion of delay isn't added by those hard blocks.
Yeah.
It's by
Yeah, so that makes sense. So let me just repeat that. So maybe it's not the hard blocks that are making, like the critical path could be in the routing. And basically it doesn't really get affected that much by the hard blocks. And yeah, that's the right idea. Basically the speed of a circuit is defined by the slowest path. The area is kind of a sum, add everything up, but the speed is defined by a max operation. So these hard blocks can actually take a whole bunch of delays that were in logic elements and programmable routing and make them go away, because you just basically made one hard multiplier. But then there are still other paths. And if some of those paths are still long, they're in the programmable routing to get to the multiplier or in some control logic, they still limit your clock frequency. So, and this is something we saw at Altera. These numbers do line up. When we put DSP blocks in, so blocks that could do hard multipliers, for designs, they are a lot more efficient, around 10x more efficient than building it in the programmable logic. So if you exactly used what we put in the DSP block, you got about a 10x area reduction for that one function. But we didn't get much speed improvement for this exact reason. There's still other critical paths in the rest of the design, so it doesn't speed you up much. Yeah? So like the programmable routing, you mean? So, yeah. So. Yeah, so that's exactly right. So we don't get the speed up with the hard blocks, but we do get the area win, as long as we actually use them. I mean, obviously, if we don't use them, then we don't. So I'll kind of end on this slide. So the hardware substrate, there's a big gap. So FPGA area versus ASIC area, depending on if it's got using a lot of hard blocks or using almost all soft logic, 4x to 35x area gap. This is a bit optimistic for ASICs, though, because in this study, they use small circuits, and ASICs they're using an FPGA that has enough routing to route big circuits. Okay, so the FPGA is paying for all that routing because it's prefabricated. The ASIC probably won't route without some white space addition. So typically you need around, this varies depending on your design, but typically maybe 40% white space in a big ASIC design over the cells to actually route it successfully. So this is probably a bit optimistic, but even if I bloat the numbers by 40%, for this one that was most of the soft logic, still a big gap, 4x to 21x. Speed was about 3x. If I want to know how much throughput I get from a certain unit of silicon, I multiply the area and the delay together, right? I can get more throughput by putting more units in. So smaller area gets me more parallelism, or I can clock faster. So area times delay is essentially the opposite of throughput. And the area delay gap here is big. So I get 12x to 60x. This is probably, this is when I'm using lots of hard blocks. So that's the case that's going to be more interesting for most FPGA users. There's a more recent study done by one of my grad students where he took neural network accelerators, convolutional neural network accelerators, so more modern designs. And he found that the area gap for an FPGA was 8x. And the delay gap was 4x. And this is a mix of hard and soft blocks. So it is within this range. Now, he's comparing to a non-programmable ASIC. So he basically, this is like a limit study, because he's taking one CNN and building a hardware circuit in an FPGA or an ASIC that can do exactly that one thing. Now, in an FPGA, you can do that, because you can reprogram it to do other stuff. But in an ASIC, you would never really do that, because if anybody changes anything about that network, your chip is done. Right? And you just spent a huge amount of money on it. So it's a correct result, but the fact that the FPGA is programmable means you could build this, whereas in the ASIC, you're going to put more programmability in this. The other thing to remember is that FPGAs use the latest process technology because they can. They're programmable, so their total market is pretty big, so they can go to aggressive process nodes. So Intel's latest FPGA is on 10 nanometers. Xilinx is on either 10 or 7. They're in the middle of moving it. The average ASIC is several generations behind that. So typically, not the leading edge, right? Like, so GPUs, processors, they're on the leading edge. They're at like 7 nanometers. But the typical special purpose chip is 3 generations behind because it takes them longer to design it and they don't have the money. If you're 3 generations behind, so instead of being at 7 nanometers, you're at 22 nanometers, that's actually an 8x density loss, and it's harder to calculate, but it's about a 1.5x speed loss typically. It depends on the process details, but that would be a reasonable number. That's about a 12x area delay penalty. So if you start comparing the ASIC you would likely build if you're not in an enormous market versus the FPGA you could buy, it's more like you're around parity if you're going to use a lot of the FPGA hard blocks to you are significantly worse if you're just going to use the programmable logic. Does that make sense? This is part of why the FPGA manufacturers are some of the early adopters of next generation process technology. They can, because they have a big enough market to justify it, and it helps them close this gap so they can sell those chips well. Okay? And that's as far as I was going to go today. What I was going to talk about at the start of next week, is the last part of this lecture, is the other paper that you were assigned this week, which you still have till Saturday to read and write a summary of, is basically trying to assess what is the overhead. I shouldn't show you that. That makes it too easy to do the summary. What is the overhead of an instruction stream? Okay, so the overhead of FPGA-style programmability is large, particularly for the soft logic. The overhead of an instruction stream in a processor is also large. So there's no getting away from it. Costs a lot for programmability. And that's what the other paper that you were to read this week is about. So we're going to try to take that and put it together into some overall comparisons. Okay, thanks everybody.